along with we will discuss two important subgroup. One is center of a group and centralizer of an element in a group. So for any two groups, you will see this kind of subgroup. Okay, we'll start from the definition of subgroup. So here our definition is, let G naught be a group. Here naught is the basically binary composition, and H be non-empty subset of G. Non-empty subset of G. Then H is called a subgroup of G. Subgroup of G if H with respect to the same operation, same binary operation, is a group. Okay, so G, we just consider here E. It contains the same identity element. So here one important note: if H is a subgroup of G, and E is the identity element in G, in G, then we must say E must belongs to H. So if if the identity element does not belong to H, then you can easily say H is not a subgroup of G. Now we'll do the subgroup test. Here our next recall is about subgroup test. So what you will do, let G be a group and H is basically subset of G. So what you will check? First you will check E belongs to H, and that implies H is non-empty subset of G. And second, AB belongs to H for all AB belongs to H. And third, A inverse belongs to H for all A belongs to H. If it holds, then we conclude H is a subgroup of G. Okay, this is one way, or you can check in different way. You can make the last two condition into one condition. So let G be a group, and H is a subset of G if first one is H is non-empty subset of G. That means you will check E belongs to H or not. Okay, just you will check it. And second, AB inverse belongs to H for all AB belongs to H. In that case, again we can conclude H is a subgroup of G. So we'll start one important question, and that question asked in Calcutta University Math Honours Examination. The question is, in a group G, the question is given in the year of 2006. This question is in our case 33. In a group G, if AB whole cube, this is equals to A cube B cube for all AB belongs to G, then show that the set H equals to all the element of the form X cube such that X belongs to G. This set is a subgroup of G. Now how to solve this kind of problem? So now we'll come to the solution. What is exactly given? So here it is given G is a group, and where AB whole cube equals to A cube B cube, that holds for all A belongs to G. Okay, so it is given in a group G, AB whole cube equals to A cube B cube for all AB belongs to G, and it is also given the set H. H contains all the elements X cube pattern, where X cube is an element, X is an element of G. Now what we have to show? We have to show that H is a subgroup of G. That we have to show. So here the first step, what we will do, step 1, first we have to show that H is non-empty. Okay, so here, since E, that we can represent E cube and E both will be same, E composed E, where E is the identity element in G. So from that we can write E must be belongs to H, and hence we conclude H is non-empty subset of G. Now we come to step 2. What we will show here, we have to show that A inverse B belongs to H for all AB belongs to H. That we have to show. So okay, we will consider here, this is our G and this is H, and we have seen the identity element must contains in H, because E can be written as in the form of E cube. So now we will take two elements here, A, B. Let A comma B belongs to H. Now we just see the set H. H is in the pattern of, the element pattern is X cube. So then A must be in the form of X cube and B must be in the form of Y cube for some X comma Y belongs to G, as it is belongs to H. Okay, so now we will continue from that element A inverse B, that we have to show this element belongs to H. So what is A inverse? This is X cube inverse and Y cube. That we can write X inverse whole cube Y cube. Why? Because X cube inverse, that we can write X inverse. So that we can write X inverse. That means X inverse whole cube, and that holds for all X belongs to G. Okay, and here we can write this will be X inverse Y whole cube, because it is given AB whole cube equals to A cube B cube for all AB belongs to G, and here X belongs to G, Y belongs to G. That implies X inverse belongs to G, Y belongs to G, and by the closure property X inverse Y belongs to G. So that's why we have written here that belongs to H. Why? Since X inverse Y belongs to G, as X inverse comma Y both are belongs to G, as G is a group. So what we have seen, A inverse B belongs to H, and here we have taken AB is arbitrary element of H. So that means that relation holds for all AB belongs to H. Since A comma B belongs to H, that element are arbitrary elements. Okay, so we have done the second steps. H is non-empty subset of G. The inverse G belongs to H for all AB. So thus we conclude H is a subgroup of G. That we can say easily. Okay, now we come to the next important subgroup. This is called the center of a group. So if we think about some important subgroup of a group, So one of the important subgroup is the center of a group. So now we come to the recall. Recall is about center of a group. What exactly mean by the center of a group? So here the question that is asked in Calcutta University examination in the year of 2009. What was the question paper? The question paper is define the center ZG. That center of a group is represented by ZG. The center ZG of a group, G, and show that it is a subgroup of G, and show that it is a subgroup of G. And this is for 1 plus 2, that means 3 marks. Okay, so now we'll come to the solution. So first we'll define the center of a group G. Okay, so let G be a group, then the center of G is denoted by ZG, and is defined by, so this is your group, and that you can consider as, so here one element must be the identity ZG, defined by ZG, denoted by ZG and defined by ZG equals to all those elements in G such that is commutes with every element of G. So Ax equals to Xa for all X belongs to G. Okay. So here you just observe the elements. If one element belongs to ZG, so here the observation. One. If say let G belongs to ZG, it belongs to center of element. That means G commutes with every element. So G X equals to Xg for all X belongs to G. So if an element belongs to the center, that means it commutes with the every element of the group. This is a nice features of the element of a center of a group. Second observation, you will check the E must be belongs to ZG. Why? Because Ex equals to Xa for all X belongs to G, where E is the identity. So E must belongs to ZG, and that implies ZG must be a non-empty set. So now we'll come to the second part of the question paper. It is a subgroup of G. So this is probably the first part. This is the first part of the question, the center, the definition. And the second part, what we have to show, ZG, the center of a group, is a subgroup of G. We have to show ZG is a subgroup of G, of the group G. Now the question is, what is ZG here? The center of the group. What we know now. So here ZG is basically all those elements A belongs to G such that Ax equals to Xa for all X belongs to G. So first we will show, step 1 will show ZG is non-empty. Step 1, since E is the identity element, in G, and Ex equals to Xa, this is exactly Ex equals to Xe, this is equals to X for all X belongs to G. And that implies E must be belongs to the center of the group, and that implies ZG is always non-empty. Okay, so what we conclude here, ZG is non-empty subset of G. So this is our first step. Step 2, what we will show? Step 2 will show for all AB belongs to G. We show that here we show that A inverse B belongs to ZG for all AB belongs to ZG. That we have to show. Okay. So we just take any two element. This is our G. This is just ZG. Will take any two element. A and B belongs to ZG. So let AB belongs to ZG. Since AB belongs to the center of the group, that means A commute with every element of G and B also commute with every element of G. So then what we can write, AX equals to XA for all X belongs to G, and BX equals to XB for all X belongs to G. Okay. So now what we have to show? Now we have to show A inverse B belongs to ZG. So what exactly means? That means we will show A inverse Bx, that will be X A inverse B. If we show that, so on that case we can prove. So we'll start from A inverse Bx. So that we can write A inverse of Bx by associativity. By associativity. Okay, this we consider 1, this we consider 2. So A inverse X, that we can write A inverse Bx means XB. Why? By 2. By 2, what we have? Bx equals to XB. And from that, A inverse, so X we can write X inverse B, because since we know X inverse, this is equals to A, X as X belongs to G. And from that, we can write X inverse A inverse, X inverse A whole inverse. Okay, or X inverse A whole inverse to B. Since what we know say alpha beta whole inverse, that will be beta inverse alpha inverse for all alpha beta in G. So X inverse A, since A belongs to G, that we can write A X inverse B. Why? Because since A belongs to ZG and X inverse belongs to G, that implies A X inverse equals to X inverse A. And from that we can write X inverse A inverse B. Okay, and X inverse means this is basically X A inverse B. Okay, so what we have proved here by associativity, and we know X inverse, this will be X. So what we have proved, A inverse Bx, this is exactly equal to X A inverse B. That we have proved here. That means A inverse B belongs to ZG. Okay. So what we have proved, AB belongs to ZG, that implies A inverse B belongs to ZG. Now since AB was arbitrary, so what we can write, A inverse B belongs to ZG for all AB belongs to ZG. And therefore, by step 1 and step 2, what I conclude? We conclude that the center of the group ZG is a subgroup of G. Subgroup of G. Okay. Also, you have asked this question. The question is asked in the year of 2011. What was the question? The question is, let G be a group. Let G be a group and ZG be the subset of G. ZG be the subset of G. Defined as follows. So ZG equals to all those A belongs to G such that XA equals to AX for all X belongs to G. Then prove that ZG is a subgroup of G. Is a subgroup of G, and this is also for 2 marks question. So the same question is given. This is question number 35. The same question is given. So the solution is basically self-in exercise. Because I have already solved this problem here. So you just copy and paste here, and you can solve it easily. Now we'll come to another important subgroup. This is called the centralizer of an element. Okay. So now we'll come to another important subgroup. Let's recall. This is called centralizer of an element in a group. Of an element in a group. Now how to define? So first we'll move to the definition. Let G be a group and A is an element of G. So you have given a group G and E is an element. Then the centralizer of A is denoted by CA and is defined by CA equals to all those elements of G such that which are commute with A itself. XA equals to X. So which are commute with X only, that A only, that comes under the centralizer. Okay. So here the note 1. So if you have given B belongs to C, what exactly means? That means BA equals to A. That means B is commute with A. And it is if and only. Note 2. Since you will see EA equals to AE. Okay. Where E is the identity, where E is the identity element in G, identity in G, and from that we can write E must be belongs to CA, centralizer of the element. So that means this set is basically non-empty subset of G. Okay, now we'll prove the centralizer of an element is a group. So here the question is, that question is also important in the graduate level examination. So let G be a group and A belongs to G. Then the set, then show that the set H equals to all those X belongs to G such that XA equals to AX So this is exactly the centralizer of A. This is a subgroup of G, and this is basically 3 marks question. So this question is, in our case, this is question number 36. So now how to solve this kind of problem? What is exactly given? Here given G is a group and A is element of G. It is also given the set H. H contains all the element of G which commutes only A. So XA equals to AX. So what we have to show for subgroup, step 1, we have to say H is non-empty. So since E belongs to G, is the identity element. And EA equals to AE, this is exactly A. That holds because E is the identity. So what we can say, E belongs to H, because it maintains the condition here. Okay, and hence we can say H is non-empty subset of G. So step 1 is done. We have proved it is non-empty. Step 2. What will show? Step 2 will show we have to show that A inverse B belongs to H, or all AB belongs to H. That we have to show. Okay, so we'll consider, so this is our G, this is our H that contains E, already we have shown. We have take any two elements A and B. So let AB belongs to H. Then we must say, okay, so this is not AB, I'll take say XY. Because A is already there, we are doing XY. XY belongs to H. Since X belongs to H, so XA equals to AX and YA equals to AY. Now what we have to show, X inverse Y belongs to H. That means we will show X inverse YA equals to A X inverse Y. That we have to show. So I will start from that condition, X inverse YA. Okay, so that we can write X inverse YA by associativity. So YA means AY, so X inverse AY. Okay, so X inverse AY, that we can write, this is since YA equals to AY, and that we can write X inverse A, so that we can write X inverse A inverse whole inverse of Y. Since A inverse, this will be A for all A belongs to G. That we know. From that we can write it A inverse X whole inverse Y. Again, since X belongs to H and A inverse belongs to G, so that implies X A inverse equals to A inverse. So we can write it X A inverse whole inverse Y. And from that we can write it A inverse X inverse Y. So that means A X inverse Y. Since A inverse equals to A and AB whole inverse, that will be B inverse A inverse. For all AB belongs to G. So that means what we have proved, X inverse YA equals to AX inverse Y. That means X inverse Y belongs to H. So since XY is arbitrary, so what we can conclude, X inverse Y belongs to H for all XY belongs to H. And hence, we can conclude H is a subgroup of G. By step 1 and step 2. That we can conclude by step 1 and 2. Okay. Now we'll continue another important subgroup. The subgroup is called spatial linear group. And as we know, so here the recall is general linear group. This we represent GL2R. What is GL2R? GL2R is basically all those matrices in the form A, B, C, D, such that all A, B, C, D are real number and determinant of A is non-zero. So that means the matrix of the form A, B, C, D belongs to M2R. All entries of real and AD minus BC is non-zero. So this is basically GL2. And you will check, or it is easy to check. It is easy to check that GL2R is a group with respect to matrix multiplication. That means closer associative existence of identity inverse, all are basically whole. That we proved in some earlier classes. Now we define another set. Recall, we define another set. Define a set. The set is basically called SL2R, spatial linear group. This is basically all those ABCD belongs to GL2R such that determinant of A, that means AD minus BC, this is basically 1. And we'll check, it is easy to check that, SL2R is a subgroup of GL2R. Okay, that we can check easily. So here the question is given. Question 37. What was the question? Let H be the set of all 2 cross 2 real matrices H equals to A, B, C, D such that determinant of A, B, C, D, this is equals to. Then prove that each is a subgroup of GL2R. GL2R is basically the group of all non-singular matrices, all non-singular, because determinant is non-zero, non-singular matrices of order 2, and that will be subgroup with respect to matrix multiplication. So this is also an important question, and this kind of question you have asked in the graduation level. So now we'll come to the solution. So what we know about GL2R? This is basically all the matrices A, B, C, D belongs to set of all real matrices such that the determinant of ABCD, the determinant is basically AD minus BC is non-zero. And whereas you have given the set H, is all those ABCD belongs to GL2R. So as the determinant is 1, determinant of ABCD, that means AD minus BC, this is equals to 1. What we have to show? We have to show that H is a subgroup of GL2R with respect to matrix multiplication. With respect to matrix multiplication. So what we will check here, since the identity element, the I2 equals to 1001, is the identity element in the group GL2R, and what is the determinant of I2? This is basically 1. So what we can say, I2 equals to 1001, that must be belongs to H. And hence, H is basically non-empty subset of GL2R. So this is basically our step 1 that we have done. H is non-empty. Step 2, what we will prove? We will prove we have to show that A inverse B that belongs to H for all AB belongs to H. Okay, so that we have to show. So this is your GL2R, this is your H, and you have seen the identity element I2 1001, that must be belongs to H. So we'll take two elements, one is A and other one element is B. So let us consider two element A. A is just, you consider A is your A, B, C, D, and B is your, say, E, F, G, H. Both belong to H. Now what we can say, since they are belongs to H, so they obviously belongs to the element of GL2R. And then what we can say, determinant of A equals to 1 and determinant of B equals to 1. Now what we have to show? We have to show A inverse B belongs to H. That means we have to show determinant of A inverse B, this is basically 1. And A inverse B is an element of GL2R. Okay. So now A inverse B, so since determinant of A is 1, this is non-zero, that implies A inverse exists, and determinant of A inverse non-zero, and determinant of A inverse, that means 1 by det A, and this is also non-zero. In fact, non-zero, and that implies A inverse belongs to GL2R. So now we'll start, and therefore A inverse B, that must be belongs to GL2R. Okay, as by closure property. And now we'll calculate the determinant of A inverse B. That will be det of A inverse into det of B. because we know determinant of xy equals to date x into date y if x and y are both 2 cross 2 real matrices. So that we can write 1 by date A into date B. So that means it will be 1 by 1 into 1. So that's determinant of inverse B 1 and inverse B belongs to. So inverse B belongs to H. Since AB is arbitrary, so what we can write inverse B belongs to H for all AB belongs to H. So thus, so this is our step 2. So thus by step 1 and step 2, what we conclude? We conclude that inverse H is a subgroup of GL2. So this H is basically the SL2 group, a spatial linear group. Okay, so these are the few important subgroups that we have discussed in the subgroup topic, and this question is important for the graduate level examination. Okay, now we'll come to some important property of the subgroup. So one important property, so this should be the question 38. See, and this question is asked in the year of 99. What was the question paper? The question paper is true or false. True or false. The question is the intersection of two subgroup of a group. The intersection of two subgroup of a group is also a subgroup. Okay. So this question is asked for 2.5 marks. So that means you will see the different properties if G is a group and H1, H2, B2 subgroup of G, then the intersection, so this is the intersection part. This intersection is basically H1 intersection is 2, so it is a subgroup of G that you have to prove. So solution, here you will see the statement is true. The statement is true. Why it is true? Because we need to prove. We will consider two subgroup. Say here let G be a group, so we need justification. Let G be a group and H1, H2 be any two subgroup of G. Any two subgroup of G. Then what we have to prove? So we have to prove that their intersection, that means H1 intersection is 2, that we consider as H, say H is a subgroup of G. That we have to prove. So first we will show that H is non-empty. So we have step 1. Since H1 and H2 are two subgroup of G. So we must have E belongs to H1 and E also belongs to H2 as is the identity element. Is the identity element in G. And from that we can write E belongs to H1 intersection H2. And that means E belongs to H. And therefore H is non-empty subset of G. Now we come to step 2. What will show? Step 2, we show that A inverse B belongs to H for all AB belongs to H. Okay, so we'll take let A comma B belongs to H. So then here H means H1 intersection H2. And that implies A belongs to H1, B belongs to H1, or you can write A comma B both belongs to H1 and A comma B both belongs to H2. Okay, so what we will show, what is our target? A inverse B belongs to H. That means we will show A inverse B belongs to H1 intersection H2. That means we will show A inverse B belongs to H1 and A inverse B belongs to H2. That we have to show. So since AB belongs to H1 and H1 is a subgroup of G, so we can say inverse B belongs to H1. And we also say because since H1 is a subgroup of G and A comma B both are element of H1. Again, A inverse B is also subset of H2, belongs to H2. Since H2 is a subgroup of G, and A, B both are belongs to H2. So from these two conditions, what we can write? So that means we can write A inverse B belongs to H1. So inverse, what we have proved here? So A inverse B belongs to H or all AB belongs to H. Why? Because AB belongs to H, that is arbitrary. So that means, therefore, by step 1 and step 2, therefore by step 1 and 2, we conclude that H equals to H1 intersection H2 is a subgroup of G. So thus, what I conclude, intersection of any two subgroup of a group G is also a subgroup of G. So here the statement is true. So I said it is true. If we ask intersection of finite number of subgroups, it will be subgroup or not. So in question 39, we prove that finite intersections of subgroups of a group is also a subgroup of a group G. That we have to prove. So that means you have given a group and you have given the different subgroup H1, H2, H3, H4, H5 and Hn, H1, H2, H3 and so on, Hn minus 1. So this is basically the intersection. We have to show that intersection, H1 intersection H2 intersection Hn. That means you have to consider Hi is basically H is intersection of Hi, I equals to 1 to n, and you will check it is a subgroup of G. So this is your self exercise. You can solve it easily, and you will prove that intersection of finite subgroup is also a subgroup, as we proved here. intersection of two subgroup is subgroup. In similar way, you can prove intersection of two subgroup is finite number of subgroup is also a subgroup. Now the question, this is question number 40, and this question is asked in the year of 2000. So what was the question paper? In the year of 2000. Calcutta University based examination. The question is true or false? True or false? If H and K are two subgroup of a group G, if H comma K are two subgroup of a group G, then H union K is also subgroup of G. Then the union. Initially I have taken intersection, now union is a subgroup of G. And again you will see here the statement is false. The statement is false. So why it is false? We need justification, but what we see here, the union of two subgroup may not be subgroup, where intersection of two subgroup is always a subgroup. So okay, we'll set the counter example. Counter example. Let G equals to Z plus the set of all integers that we know with respect to addition is a group. Then G is a group with respect to addition. Okay, this is the additive group, and we take two subgroup. One is H1. This is basically 2Z plus, and H2. This is 3Z plus. And we will check clearly H1 and H2 are two subgroup of G. Okay, but here you will see H1 union H2, that means 2Z union 3Z. This is not a subgroup of G, because since 2 and 3 both belongs to 2Z union 3Z. Thus 2 belongs to 2Z and 3 belongs to 3Z. But 2 plus 3, that means 5, that does not belongs to 2Z union 3Z. That means H1 union H2. So that's why it is not a subgroup. So closure properties does not hold. So from that we can say H1 union H2 is not a subgroup. Okay, so here I have taken H1 H2. So you can take here H and K, because in the question it is given H and K. So I just change the question here. If H1 and H2 are two subgroups, and H1 union H2 is a subgroup. So again statement is false. So obviously it will be false if we take the finite union or arbitrary union. So arbitrary union or finite union of subgroup may not be subgroup. Thank you so much.